So welcome all. So our next speaker is Jiaqi Liu, who would be speaking on fuzzy search algorithm and how and when to use them.
Great, thanks for the intro. So last session of the day, so hopefully I won't keep you guys too long. I'm going to be going over fuzzy search algorithms today and going through a couple of examples. All the content for the examples I'll go through is on my GitHub. You can check it out there, and that's my Twitter handle, although I recently rediscovered Twitter. A little bit about myself. I am a software engineer at Button. Button is in a startup in New York City in the mobile affiliation link space, and we are connecting apps together to bring a whole new on-demand experience. So check out our tech blog over there at blog.usebutton.com. I also have stickers, so feel free to come up at the end of the session for those. The overall agenda for today, I'm going to go over a couple of common fuzzy search algorithms and go over their implementation in Python, and then also the search functionality that's built into Postgres. And then I'm going to go over the difference between syntax algorithms versus semantic analysis. So going into why this matters. Prior to my role as an engineer at Button, I was a data scientist. And nowadays, when you work as an engineer or as a data scientist, you kind of can't avoid data anyway. And when working with data, context is really important. It's not just enough to know a snippet of information, but you also have to sort of know where that fits in. And that's where a lot of the qualitative data comes in. And with qualitative data, it gets very messy very quickly. So you can have basically various forms of how to say one thing, and then suddenly you have this entity resolution issue where you have different versions of the same thing. For instance, maybe in terms of abbreviations, you can abbreviate the US as US or USA, and granted there are standards for the very reason that entity resolution is hard, but what do you do when your data is messy and is very tricky? So that's where fuzzy search algorithms come in. They're a tool to help you with these kind of problems, but not the end to the means themselves. So I'm going to start off with talking about phonetic algorithms. This is very straightforward in terms of identifying strings as how they sound in a particular language, and in this case, the English language. So the American Soundex decoding is very, very straightforward. It's actually this chart right here, and it's a very deterministic algorithm, and you can implement it yourself, or you can use a library. Here I'm going to demo a library that I use called Jellyfish. Oops. Okay. Oh. Excuse me 1 second. Okay. Oh, forgot that my screen is elsewhere. Let's go. Okay, let me make this slightly bigger. So in the Soundex engine is built into the Jellyfish library. So if you try something like Portland with fully spelled out and Portland spelled without the O, you'll get these encodings associated with them. And every Soundex encoding is a 4-character encoding, starting with a letter and then 3 numbers. So in this case, you see that the 2 strings here are actually identical in terms of how they sound. If you want to look at an example where there's a word and then maybe trailing characters following it, you'll see that it's still the same encoding, because if you remember the Soundex chart, it doesn't take into account numbers and characters that are not letters. So that's one of the issues that you might run into with Soundex. So if you look at accept versus accept, you'll see that they clearly have very similar sounds. So they actually have the same numerical value, but they have different starting letters. So that's something that's taken into consideration by this one. And for homophones, they are, again, identical. Let's see, here's another example, fourth versus the numerical fourth. And Postgres very nicely has this built-in fuzzy search algorithm functionality, and the fuzzy string match actually uses the Soundex algorithm. So I set up a local database called PyCon. Let me connect to it using SQL Alchemy. And here's like a very basic query that's very much saying, for these two strings, calculate the difference between them. And this isn't actually querying a database of any sort. It's just running this one simple query. And you'll see that it calculates the Soundex encoding, and it also calculates the difference. And the way that Postgres handles that difference is it's consider how many characters matched exactly for the encoding. And in this case, 4 means that it's a perfect match. OK, so that's not very interesting to play with without any real data. So I downloaded all of the packages on the PyPy server, their package name and their description, and loaded it into my little local Postgres database. So now I can query this table and search for every package that sounds like fuzzy search. And this is what I end up getting. And you'll see that I actually get some fuzzy sorting, fuzzy searching. Facehugger is kind of weird. OK, so let me search the descriptions, because those have a lot of really interesting data. And you'll see that in the descriptions, OK, I guess somebody created a lot of fake servers for testing. But there's also like the fuzzy search with the Postgres Trigram extension, which is exactly what I'm doing. Yeah, so the other nice thing about the search functionality is you can set the threshold for what your tolerance is. So I think the default is obviously 4, a perfect match is great. But here, if I set the threshold to be, I only care if 2 of the characters in the encoding match, then I get a lot more results that might not match as well. Versus, let's see, if I set this to 3, I get a better result. So that's something that you can play around with depending on what your particular use case is. And I can also try, I think debugging is like a really interesting thing. So let's try it to see what kind of debugging libraries there could be. Oh, and it's very interesting to see that debugging is also sort of similar to, I guess, device and things like that. All right. Oops. Moving back to slides. So the pros of Soundex are that it's very easy to implement. It's deterministic, so you always know what you're getting back. Some of the cons are it's very limited to the language, to the dialect. It's computationally fast, which I'll cover more later. And the con there is that it only takes into consideration letters. So all those version numbers associated in the PyPy database, like what happens to those, et cetera. And it's very limited in terms of how it calculates distance, because there's only 4 coding values. So what happens when you care much more about the distance between words? And what does that mean anyway? So one way to evaluate distance is the Levenshtein distance, also known as the edit distance, which means how many changes do you have to make to a string to get to another string. And those specific changes are defined as you can have a deletion, deleting a character. You can have an insertion, inserting a new character into a string. or you can have a substitution, so swapping out a character for a different character. There's a different types of Levenshtein algorithm called the Damaru-Levenshtein algorithm, which includes also a transposition between two characters that are next to each other, so swapping two characters. Let's move to the IPython demo. All right. So here again, I downloaded a library, and this is also a deterministic algorithm. And here you can see that for Smith with the Y versus Smith with the I, you only need to change two characters to get them to be the same. For PyPy, it's 1 for changing one little character. Some of the pitfalls here are that it gets really tricky. Say you're comparing two addresses, and you know that 99 Broadway is probably really close to 100 Broadway. So in terms of your concept of distance for addresses, that's kind of what you care about. But in terms of you look at this, 99 and 100 have an edit distance of 3, but 99 and 999 has an edit distance of 1. They're a lot closer in terms of string similarity, but the notion, because we understand the notion of addresses, they're actually further away. So in this scenario, you actually want to customize your edit distance calculation, maybe weigh numbers differently than letters. Yeah, so here 999 and 100 is the same distance as 99 and 100. Another issue is in terms of when you have longer strings. Here you have Mike's New York Deli & Co., Sam's New York Deli & Co., and the edit distance here is actually the same as if this were a shorter string. And depending on what kind of analysis you're doing, maybe that is the use case that you want to go with. That is correct in terms of how you want to analyze this data. But it could also mean that you actually care more about when it's a smaller string and there's a bigger difference. So you might want to weigh your edit distances based on the length of the overall string, in addition to just the edit distances that you would have to make. Yeah, so converting raw edits, penalize long strings, and being able to weigh numbers differently are fun things you can do with Levenshtein to customize your algorithm. So let's move to the next topic. And this is the comparison between, I guess, those two when you swap letters. Yeah, pretty easy to implement, computationally fast, but it's always a pairwise comparison, which means which pretty much constrains you to making comparisons between two strings and then making more comparisons, et cetera. And you might need to customize depending on your use case. N-grams. So this is my personal favorite. And trigrams. It's slightly different from the phonetic search and the edit distance because it takes into consideration a lot more components of the word. So instead of one letter or one character at a time, it sort of takes into consideration the characters preceding the other characters. And you can customize it to see if you want a unigram or bigram. Trigram is the most common one, and Postgres has a wonderful built-in trigram search. And let's take a look at the demo. OK. So I wrote my own tokenizer, but a lot of the open source libraries, again, have a lot of tokenizers are easy to come by. And here's what tokenization for a sentence would look like in terms of the grams being words. And let's see. Here's what tokenization for a string would look like. In terms of calculating similarity, there's a lot of different ways that this can go, but I've typically seen the Jacquard similarity being used, which is the intersection of over the union. So in this particular case, if you find the intersection of two gram arrays, for here, yeah, this is how I would define the function. And if you use the same array, you would get a perfect score of 1.0 because you're comparing two exactly same strings. And here I have two slightly different strings, and you'll find that I get a slightly less score. So this is This is a really useful score for doing further analysis. Trigram with Postgres. So again, Postgres has a built-in Trigram functionality. And I'm going to use the same database that I was using earlier with the PyPy packages. Connecting to it. And here I'm going to search the description for the similarity between two different strings. Let's see if I can. OK. So the way that this query is structured, it's querying the PyPy table on the description column, and it's going to take in as input the script string. And let's run this. OK. Let's see what this looks like. OK, cool. And then here are the results that I get. And I also get a trigram score associated with it. So the built-in Postgres functionality cuts off the score at 0.3, which is why you don't see any values below 0.3. Otherwise, you could basically have anything that's a score of 0. All right. So now I'm going to run the same query over the package column. And let's see. And here I am going to, so I see that I have some really high scoring ones, and something I can do to basically customize how I want to interpret this data. And this limit can be added to the query string itself or in Python, but I can cut off the query to be at, I'm only willing to tolerate a score of 0.5 or above. And then these are the results I filter down to. So what this sort of brings us towards is that you can use the score from the Trigram search, and you can use the score from fuzzy search to do other things, to build other algorithms. So here it's a very simple heuristic, but you can actually use it as a feature in the statistical model, which in itself is an entirely different talk. But this is very much a stepping stone towards getting you to your end goal, as much as it is about also figuring out how to analyze qualitative data. OK, let's see if I can search debug. And there's a lot more results here. It's very interesting. All right. So that is more so on the, leveraging Trigram as sort of as a stepping stone for bigger analyses. And then you can also build statistical models on top of the score as a feature. Something to note is I only have about 122,000 records in my table. So my data set isn't very large. But even so, the query that was the AND query, that was 0.48 by milliseconds. And then the Soundex query on 100K records was actually 44 milliseconds. And even scarier is the trigram query. So if you think about it for trigram, it has to calculate the n-grams for all of the strings in the table and evaluate the similarity there. So when I ran a analysis on the query within Postgres, the execution time was actually 867 milliseconds, which is kind of scary in terms of how long that takes to run. Some things to tackle there are Postgres has these just-engine indices, and you can create just-engine indices to pre-calculate your n-grams for larger tables, and this actually helps with performance a lot. For my really small table, it doesn't really improve performance that much. Yay, more context for trigram search. Instead of handling one character at a time, you're actually taking into consideration a combination of characters and also their neighbors. You can determine what your proper unit of analysis is, one character at a time, or two, or three. But it is slower to calculate, especially on the fly, and it is slower to search in general. Okay, so this brings us to semantic search. Yeah, all this phonetic stuff is super helpful, and it gets you one step further. But what happens, if you want to take into consideration the meaning of the words? And this is pretty interesting in terms of, this is why the context for semantic stuff matters, is I'm sorry and my bad mean the same thing. But not really, unless you're at a funeral. Sad. And I'll show you two examples today, nltk and word2vec. nltk has WordNet as its built-in corpus. And the very simple code snippet that I have here is if you look for two words within nltk, you can actually sort of calculate the similarity between those two words. And blue and green, both colors, and they're pretty similar there. Word2vec is it's from Google, and actually now it's part of the TensorFlow library. It allows you to basically train a corpus in a neural network and to maximize the conditional probability to take into context of the meaning of a word. And then you use the trained model to generate the vector form of each word. And then once you have the vector form of a word, you can actually use that to perform all sorts of calculations, and you can use that to find similarities. And a very common example is when you see the king vector, the man vector, the queen vector, you often see the example where king minus man plus queen equals woman, or actually king minus man plus woman equals queen. And yeah, word analogy is a very fun way to interact with word vectors. So an example that I have is breakfast minus sunshine, and plus nighttime equals dinner. So I know you guys are thinking about dinner already. And yeah, let's see the example I have here. Okay, so I kind of cheated a little bit, and I pre-trained the model. Otherwise, that takes a little bit of time. And I used a very generic corpus. Something to note is, depending on what your use case is, what your scenario is, your corpus matters a lot. And here I just used a very generic one, and this is the vector representation of the word coffee. Okay, and then I can actually get words that are considered similar to coffee and the distances between them. So here, the distance is actually calculated as the cosine distance between two vectors. So coffee is very close to wheat and cotton and beef and such. Let's see what I get when I type in Python. Oh my God, this is, I had not expected that, because you never know with corpuses whether they interpret Python as like the snake and animal or as the language. So Python is close to PHP, and I don't know if that offends or makes people feel good. Okay. All right, and this is the example for the word analogy. So coffee plus night minus day, I get tea, and all sorts of quirky things. Let's see, I have the sun plus cold minus warm. You get moon and things like that. All right. Let me go back to the slides. So fuzzy search is very powerful for adding context to qualitative data, and also for turning a lot of your qualitative data into quantitative data, so you can do more with it, like build models or rank things. It can be used as a stepping stone to broader analysis, or if your purpose is to just search for things, it's a very powerful search mechanism. And you can customize a lot of the syntax use cases for things that for whatever your use case and scenario is, you can also customize the semantic search ones by building out your own corpus and training on that. And yeah, that is it for my presentation. Again, you can find this content on GitHub, and feel free to ask questions or follow up afterwards. Thank you, guys.
So we still have time for questions. So if anybody has a question, please queue up here to the mic.
So first of all, thank you very much for the talk. I had a question regarding the Soundex. So I already had experience with like trigrams and n-grams for building naive-based classifiers. Probably a simple example would be like spam detection and stuff like that. But I wanted to know if you or anyone else here had experience using Soundex to generate features for a naive-based classifier or something similar.
Yeah, I think, so in my experience, I worked a lot with abbreviated data. So that's where Soundex, and there's another library, I think, called Metaphonics, comes in. And it's helpful because with abbreviated data, what happens is that a lot of the vowels are taken out. So Soundex actually becomes just better in terms of metric than something like Levenshtein or Trigram, because all the vowels are taken out, so it still like sound the same, but it's a very, very different string. So that's in terms of my experience. I don't know if anyone in the audience has other experiences with Soundex. And
Thank you.
cool.
Thanks for the talk. Yeah. So kind of knowing that there's no great answer to this question, but just curious to your approach of like threshold setting, right? When we're talking about these things, if you're doing an ordinal comparison ranking, it's fine. But if you really need inclusion, exclusion, how do you approach the problem of what do we set that at?
Yeah, I think when I started out, something that was really helpful to me was we actually like drew out this ROC curve of thresholds that we were willing to tolerate and how that affected our performance in terms of model performance and things like that. So yeah, it is very much a guessing game, and how much you're willing to tolerate and being able to tweak that on the fly. Writing code that is easy to edit later on when you change your mind about how you want to approach that threshold is always helpful as well. Cool. Yeah?
First off, thank you. This was a really excellent overview. I was just wondering if anybody had taken the step of putting the output of Soundex or anything like that into Word2Vec and trying to train with that. It seems like it might be pretty powerful. Are you aware of anything like that?
I am not aware of how that would play. I think it could be really interesting. I did play around with taking the output of Soundex and putting that through Levenshtein as like a kind of like, calculating the distance metric a different way. I think it's a little bit hard because the code is just limited to those 4 characters and how much information that can possibly provide. But that could be a fun weekend project. Yeah.
Do you know if any of these approaches can be vectorized, and if they're not currently, or at least the ones that you put up, if there are any packages that can do vectorized fuzzy searching?
So as in terms of like, other than the Word2Vec vectorization, I guess I'm not really sure how, it kind of ties into what your question was, is can you vectorize, I guess, do you mean like vectorizing as in turning it into an operation, or vectorizing like the results of like Soundex or Levenshtein?
Mainly the former.
Okay, former. Yeah, I'm not sure on that, but I imagine that somewhere on the internet, someone has tried to vectorize these as operations. It would be the intuitive thing to do.
Awesome. Thank you.
Okay, thanks. Cool.
So thank you for this wonderful talk. three speaker done.